Welcome back to Topic 35 for Algebra 1, Recursive Formulas. In Part 2, we're going to practice how to write a recursive formula given a sequence. In Topics 33 and 34, we identified that sequences can either be arithmetic or geometric. On the example on the left-hand side, we see the recursive formula for an arithmetic sequence, and we have an example. Now, recursive formulas have three parts to them. You need to identify the first term, you need to identify the pattern, and you need to identify that this pattern works for finding the second term and up. Given our sequence of -3, 2, 7, and 12, we're going to first write down what the first term is, which is -3. Simple as that. The second part, when writing the recursive formula for an arithmetic sequence, is identifying this pattern. So remember, a sub n is the term that you want. We're going to use this outline from above when writing this. So in order to get the term that you want, you need to take the term in front of it, or the previous term. In this case, we write that as a sub n minus 1, and then add our common difference. Remember, arithmetic sequences always deal with addition. We can add positive numbers and we can also add negative numbers. So I need to look at my sequence and determine what is the common difference. How do I get from -3 to 2, from 2 to 7, from 7 to 12? And it's common because it's consistent between all of these numbers. We're jumping the same amount of steps on the number line. So in order to get from -3 to 2, from 2 to 7, from 7 to 12, we're adding 5 every time. So my pattern is a sub n equals a sub n minus 1 plus 5. And this works for finding the second term and up. That last part is always consistent. It's always going to be for finding the second term and up. We don't need to worry about the first term because the first term is given. Now, trying another example on the right-hand side for a geometric sequence, we have 0.5, or 1/2, 1, 2, 4. So the first term is 0.5. In order to determine our pattern, we're going to use this outline provided above. So the term that we want, we need to take the previous term, a sub n minus 1, and multiply it by a common ratio. Now, in order to get from 1/2 to 1, from 1 to 2, from 2 to 4, we're not adding a number here, but instead we're multiplying. Specifically, we're multiplying by 2. So our common ratio is 2. And again, this works for finding the second term and up. Moving to the next part of our foldable, this is on the inside of that bottom flap. We have to do two things. We have to determine whether the sequence is arithmetic or geometric, and then also write the recursive formula. So on the first two examples we just did, it was given if it was arithmetic or geometric. But now we have to think back to identifying either the common difference or the common ratio in order to determine if it's arithmetic or geometric. Looking at the first example, we have 22, 16, 10, and 4. So looking at this sequence, we have to identify, okay, is it arithmetic or geometric? Well, in order to get from 22 to 16, from 16 to 10, from 10 to 4, if I think about those on the number line, they're evenly spaced out. So I am using the same number to jump from 22 to 16, from 16 to 10, from 10 to 4. Specifically, that number is -6. But remember, with arithmetic, we're adding. So I'm adding a -6. Now, for writing recursive formulas, we have to again identify those three parts. So the first term is 22. Then, if we want to look back to our outline, In order to get the term we want, we need to take the previous term and add the common difference. Now in this case, adding a negative is just the same thing as subtracting, so we can just write minus 6 here. But in our mind, we know that that common difference is adding a negative 6. And this works for finding the second term and up. Looking at the example below, we have 243, 81, 27, and 9. With this example, it doesn't seem like these numbers in the number line are evenly spaced out in terms of I can't use one number in order to either add or subtract to get to the following number. So this is a geometric sequence. Now I know that this list of numbers, this sequence is decreasing in value because I'm going from 243 all the way to 81 to 27, etc., etc. So with geometric sequences, I have to multiply. But because I know that this sequence is decreasing, I'm not going to be multiplying by a whole number. Instead, I'm going to be multiplying by a fraction. So we reviewed this in topic 34 in order to determine this common ratio. I can take one term and divide it by the previous term. So I can have 81 divided by 243, or 27 divided by 81, or 9 divided by 27. These are all equivalent to our common ratio if I simplify them. Now 9 divided by 27, how many times does 9 go into 27? 9 goes into 27 3 times, and since 3 is the bigger number and it's located on the denominator, that's where I'm going to write my 3. Same thing with 27 81sts and 81 243rds. So I'm multiplying by 1/3 here. Now let's write our recursive formula. The first term is 243. My pattern is a sub n equals the previous term, a sub n minus 1, times 1/3. And this works for finding the second term and up. Moving on to the middle column, we start with -8, -3, 2, and 7. Now, again, if I think about these numbers on the number line, I think that this is an arithmetic sequence. Specifically, in order to get from -8 to -3, from -3 to +2, from 2 to 7, I'm adding 5 every single time in order to jump from one number in the sequence to the next. I start with -8. In order to determine my pattern here, the term that I want, I need to take the previous term and add 5 to it, and this works for finding the second term and up. Now the example below is -3, 14, 31, 48. Now if I think in my head, I want to try to run through, okay, are there any numbers that I could easily multiply to get from one number to the next? Now this deals with kind of some funky numbers, so I'm going to test out adding. Can I add any number in order to get from one number to the next? I can. Here, I'm actually adding 17 in order to get from -3 to 14, 14 to 31, 31 to 48. This sequence of numbers is increasing, so I know my common difference is a positive number. So this sequence must be arithmetic because we have a common difference. My first term is -3. The term that I want is equal to the term right before it, plus 17. And this works for finding the second term and up. Looking at the third column, we have 5, 15, 45, 135, etc., etc. Now this, we're dealing with bigger numbers when jumping from one to the next. So I'm probably not adding the same number every time, but instead multiplying. In order to get from 5 to 15, from 15 to 45, from 45 to 135, I'm multiplying by +3. So this is a geometric sequence. The first term is 5. In order to get the term that I want, I need to take the previous term and multiply it by 3. And this works for finding the second term and up. Now I do want to mention with geometric terms, our geometric sequences, oftentimes when you see them written in a recursive formula, you might see the ratio written first and then a sub n minus 1. So for example, with this example that we just did, the pattern might be a sub n equals 3 times a sub n minus 1. Now these are equivalent because multiplication is commutative. We can flip the order and we will still get the same product in the end. But traditionally, we might see that number written first and then the variable. Think about if you have x4. You wouldn't usually see it written as x4. You would instead see it written as 4x. So same thing here. However, if it's easier for you to think back to this formula with a sub n and then a sub n minus 1, I should say, and then times that common ratio, that's all set too. Last example. We have 8, negative 20, 50, and negative 125. Now notice here how I'm jumping back and forth in between positive numbers and negative numbers. Now can I add a number consistently so that I go back and forth between those two sides of the number line? I can't. So in this case, I must be multiplying. And specifically, I'm going to be multiplying by a negative number. So this is a geometric sequence. Think about it. If you multiply a positive times a negative, you get a negative. If you multiply then a negative times a negative, you get a positive. Hence, that's why we have the sequence that is alternating between positives and negatives. Now, in order to determine this common ratio, it's a little bit tricky at first glance. But we can use the tool that we used in the second example on this slide with division and going backwards. So I can take negative 20 and divide it by the previous term. Or I can take 50 and divide it by the previous term, which is negative 20. Or take negative 125 and divide it by 50. This will get me my common ratio of negative 5 halves, also known as negative 2.5. So I'm multiplying by negative 2.5 every single time in order to get from one term to the next. My first term here is 8. In order to find the term that I want, I need to take the previous term and multiply it by negative 2.5. Now make sure here we're dealing with multiplication. So it's helpful to write this in parentheses, especially because this common ratio is negative. We don't just want to write minus 2.5 because we don't want someone to be confused and think that we're dealing with an arithmetic sequence, when in actuality we're dealing with a geometric sequence. And this works for finding the second term and up. Thank you for watching part 2 of topic 35 for Algebra 1, Recursive Formulas.